Hey everyone, welcome back to Power Electronics. I'm Tim, this is Lecture 1. Cool, so the goal of this lecture is really to introduce this thing. This is the buck converter. And in the last lecture I mentioned that this is kind of like the primordial switch mode power supply, right? This is kind of like the first one you learn about. And it introduces all the interesting concepts of power electronics in a pretty simple way. There are some complications, there's some detailed stuff you can really look at with the buck converter, but this is the beginning. So this is where we want to get. However, last time, what we were talking about was this voltage divider, right? So we used, last time we wanted to regulate a battery voltage which varied, right? So this thing, it varied from 2.5 volts up to 4.2 volts. And we wanted to regulate that to 1 volt. We wanted V out to be 1 volt at all times. So what we did was we put a resistor in series with the battery and the load, and we found that there was this relation between the input and output voltage, the battery voltage and the output voltage. And what we did was, for some VBAT, we would choose our series to force V out to be 1 volt. And again, I mentioned you could do this with you could sit there with a little rheostat, a little variable resistor, and adjust our series to force this to happen. But typically what people do is they use something called an LDO. And I'll just erase this because you can't see the full thing. So they use this thing, which is called an LDO, a low dropout regulator. And in a low dropout regulator, we're using a transistor as a variable resistor. And we compare the output voltage to some reference to adjust the gate voltage of the transistor, to adjust the voltage drop across the transistor, which in turn forces the output voltage towards the reference voltage. And in that way we can control the output voltage. Cool, so last time I noticed two things about the voltage divider, about this kind of solution. One, we can only step the voltage down. And really, it doesn't answer the question, what happens if we need a larger voltage than what's provided? The voltage divider is not able to increase the input voltage, right? So if we want 5 volts and our battery only goes up to 4.5, we're screwed. We're out of luck. The second thing is, the efficiency is poor if we want the output voltage to be significantly lower than the input. And this was because, if you recall, we found that eta was a ratio of the output voltage to the input voltage for a resistor divider, right? So what this says is that if V out is much less than V in, then eta, the efficiency, will tend towards 0%, right? We like to think of efficiencies in percentages. So if the output voltage is much smaller than the input, then this ratio will be small, which means the efficiency will be small. So let's look a little bit deeper into this efficiency. Last time we came up with this equation, but let's look into why this is happening. So let's look back at our LDO. So we have this transistor, which is being used as a resistor to regulate the output voltage. And we want to look at the loss. We want to look at where we're losing power and how we're losing power. So power consumption by resistors is really a product of the voltage across them and the current through them. So let's find the voltage across this element and the current through the element. So first, VLDO, the voltage across this device. I'll label as VLDO. Very simply, we can use KVL. We can think about this single loop, right? And we can notice that if we go around this loop, voltages which align with my direction of the loop are on the left side of the equation. Voltages which are anti-parallel to that direction are on the right side of the equation. And by KVL, the things on the left side should be equal to the things on the right side. So we have VBAT, which aligns with my arrow, is equal to VLDO. Sorry, I'll use this cursive lowercase v, which I hope you can distinguish from my regular uppercase V, VLDO plus V out. And if we rearrange this, we notice that VLDO, the voltage across this transistor, is the difference between the input and output voltage. So while this device is on, while we're providing power to the output, to this R load, there is a voltage drop across this transistor, always. And that voltage drop is always the difference between the input voltage and the output voltage. Okay, cool. So that's one thing down, right? We got the voltage across it. Next, we want to see the current through this device, ILDO. Well, there's only one loop, right, in the circuit, right? So that means that the current flowing through this transistor must also be the current flowing through this load resistor. And the current flowing through the load resistor is just I out. It's the output current. Sometimes we refer to it as I out. And I out is simply the output voltage over this load resistance. V out over R load. We force our load to be... We force V out to be 1 volt, and then the output current is simply the output voltage divided by whatever our load is. So, because there's only one loop, ILDO must be equal to that output current. The current that flows through the output must flow through this transistor. By KCL, you could say, right? You can imagine this. Again, there's an op amp, no current goes into this, but yeah, you can imagine this node, I out flows here, ILDO flows to this line. They must be equal, right? So this is V out over R load. Okay, cool. So that means that the loss across the element, the power that this thing consumes, must be the product of these two things, right? It must be the product of VLDO and ILDO. So if you write that out, we get the loss across the power consumed by this transistor is the difference between the input and output voltage times the output voltage of the load resistor. So this term is kind of a little bit deceiving because there's V out in there. If V out gets small, then the power loss should be small. But let's ignore that for now and really just notice that the power is proportional to the power loss is proportional to the difference between the input voltage and the output voltage. So if there is a difference between the input and output, then we have loss. There will be loss, right? And it's proportional to that difference. Okay, that's because we're using this transistor as a resistor, right? This element has a voltage across it at all times whenever it's on, and it has a current through it at all times whenever this device is on. That means there will be loss, and this is the expression for that loss. We noticed that this loss was not good, especially if this difference is large, right? That means that the loss will be large relative to the load power. Okay, so we don't have to use the transistor as a resistor, right? That's one option. That's kind of like the analog electronics option of using a transistor. But if we think about, say, digital electronics, we can also use a transistor as a switch, right? We can, like, what happens if we use the transistor as a switch? In other words, what happens if we use transistor in the switch mode as opposed to the linear mode? All right, I'm getting close. In switch mode. I'll just say in the switch mode. Switch mode. Cool. Perfect. This is where the switch mode of switch mode power supplies comes from. Cool. So what happens if we do this? I'll just get this out of your way. So we have the same circuit, but now instead of using the transistor as a resistor, we're using the transistor as in this case, I'm showing an ideal switch, Q. So we have two options for this ideal switch, Q, right? Either Q can be on or Q can be off. Let's look at what happens in both cases. Q on and Q off. So when Q is on, here I'll just underline this as well. When Q is on, the ideal switch is a short circuit. Right? An ideal switch when it's on is just a short circuit. That means that the voltage across this switch, VQ, is 0, right? Because there is no voltage drop across a short circuit. A short circuit is like a 0 resistance, right? So no matter how much current you send through the switch, because it's a short circuit, there's no voltage drop. So VQ equals 0 because it's a short circuit. That means if we think about the loss, I'll just write PQ, which is a product of the voltage and the current through this element. Because VQ is 0, the loss is 0. So when a switch is on, when an ideal switch is on, it dissipates no power. Cool. Okay, what happens if it's off, right? So when a switch is off, it's an open circuit. So kind of the fundamental idea of an open circuit is that no current can pass through it, right? Open circuits don't pass any current. IQ must therefore be equal to 0. And again, PQ, which is the product of the voltage across the element and the current through that element, must also be 0 because the current is 0. So when the switch is off, it also doesn't dissipate any power. So by using a transistor as a switch instead of as a resistive element, it won't dissipate any power if we use it. So how do we leverage this idea? How do we use this idea to our advantage? Well, we have another idea. The second idea, idea 2, right? Idea 2 is switch between on and off periodically, right? So instead of just having the switch Q on or off forever, instead what we'll do is go on and off at some regular intervals, right? So what does this look like? Well, to explain, I will plot the state of the switch over time. By the state of Q. By the state, I mean whether it's on or off. So state of Q. So if we're doing it periodically, we must have regular time intervals, right? So we'll have one time interval, another time interval, another time interval, and this extends forever, right? We'll just do this for eternity. As long as it takes, we'll do this, right? So this time interval we'll call TSW. And here's 2 TSW, here's 3 TSW, and TSW is our switching period. It is the length of time, so it has units of seconds, it's the length of time that it takes for us to switch between on and off. Okay, so within each switching period, we will have 2 subintervals. One where the switch is on and one where the switch is off. And sorry, just to go back, sometimes we like to think of the switching frequency, right? Which is simply the inverse of the switching period. And this is like how often we switch on and off. And this has units of hertz. People often like to talk about the switching frequency of a power converter. So we should know what FSW is. Cool, so again, we've divided our switching periods into 2 subintervals. In the first subinterval, which has length, I will say dTSW. In this first subinterval, d times TSW, Q is on. And in the second subinterval, Q is off. And then we repeat, right? So then we start a new switching period. So in this first subinterval, Q is on. And then Q is off, and on and on and on and on. That just goes on forever. So what is D? D is what we call the duty ratio, which is the ratio of the time the switch is on to the full period. T on to T switch, right? So T on just represents the length of time the switch is on, and TSW is the switching period. This is unitless. And I want you to notice that D can only vary between 0 and 1, right? So either the switch can be on for the full switching period, right? Which would mean that D is 1. The on time is equal to the switching period, D is 1. Or at the other end, if D is 0, that means that the switch is never on, right? So this first subinterval would be 0. And this D is something we can control. We can control D. And D, so this length of time, this duty ratio D, I'll just write it in a different color. D represents the pulse width of our square wave. And this, what square wave are you talking about, Tim? Well, we'll show that in the next slide. But D represents the pulse width, right? So as D gets bigger, the pulse width gets bigger. As D gets smaller, the pulse width gets smaller. Okay, and then finally, there's one other part of this switching period which I should define. So the time that Q is off is sometimes referred to as D prime. So D prime is how you'd say it, is the ratio of the off time, the length of time the switch is off, to the switching period. And if you think about how there are two states and we're subdividing this switching period into two states, if D is 1/2, or if dTSW is one part of it, then D prime must be the remaining part of it. So D prime is actually equal to 1 minus D. So because we're usually thinking about two switching state converters, this idea of D prime is something that we're going to see a lot. So you should just get used to this notation, D prime notation. D prime is 1 minus D. Cool. So this is what we're going to do. We're going to switch this Q on and off at regular intervals, and we control the length of time that the switch is on versus the length of time the switch is off. And that way we're controlling the pulse width of this square wave that we're going to create. So let's plot the output voltage, right? So what we did was, before we plotted the state of the switch, and now we're going to plot V out. And I'll use a color that you guys can see. Let's say blue, maybe a brighter blue. How about this blue? So V out, whatever this blue is, some color. Anyways, we divide time into intervals, right? Our switching periods. So we have TSW, we have 2 TSW, 3 TSW, and this goes on forever, right? Within each interval, we have 2 sub-intervals, right? So the first one is when Q is on. So Q is on here, and over here Q is off. And we repeat this, right? For the next sub-interval, again, Q is on, and then Q is off. And again, this repeats forever. So when Q is on, we have a short circuit, right? When Q is on, it's a short circuit, which means the output voltage is the battery voltage, right? There's no difference in voltage between the input and output. So when Q is on, the output voltage is equal to VBAT. When Q is off, we have an open circuit, which means that no current flows to the load resistor, and Vout must be 0. So Vout becomes 0. And then we repeat, right? The next switching period, Q is on again, the output voltage goes to VBAT, Q goes off, output voltage goes to 0, and again, we repeat. So here's our square wave, right? This is the square wave that I was referring to before. And the output voltage, if we use Q as a switch, if we use the transistor as a switch, it alternates between the input and 0. Okay, this length of time, again, is dTSW, and we control D, right? We control the pulse width of this square wave. So this doesn't look exactly like what we wanted, right? What we did with the voltage divider was produce a DC voltage. This is not a DC voltage. However, it does have an average, right? There is an average. So this isn't a DC voltage, but it has a DC component. And we'll find this DC component by averaging it, right? And we don't have to average over all of time, right? This is like a regular phenomenon. We're switching periodically. So all we need to do is switch over or average over the switching period. And the way we do that, or the way the notation I'll use to do that, is with a triangular brace. We put in the variable of interest, V out of t, right? This is a time varying signal, and we average over some interval, the switching period. So this is equal to, so to average we sum, right? It's continuous, so we use an integral. We sum from some time t to some time t plus TSW, right? This is the length of time we're averaging over. We integrate our signal of interest over some dummy variable, and then we divide by the length of time, right? 1 over TSW. Right, so this average will give us the average over one switching cycle, right? It will tell us what the average output voltage is over one switching cycle. And because this happens regularly, because we're doing this continually, or for all of time, let's say, then the average output voltage is this moving average, right? So this is right, this is how we find the average output voltage. So let's do it for this equation, right? Let's do it for this particular example, I mean. All right, so V out of t averaged over one switching period is equal to 1 over Ts times our integral. So this integral, I'm going to start integrating from time t equals 0 to, this is the time period I'm integrating over. We can choose, but it's convenient to choose starting at time t equals 0. Because this is a piecewise constant function, right? For the first subinterval, the output voltage is VBAT, and for the second subinterval, the output voltage is 0. We can split our integral up into two parts. One between 0 and dTSW, right? Up to this time. So we're integrating this rectangle. The output voltage is equal to VBAT. And we integrate over our dummy variable, right? And the second subinterval is from dTSW up to TSW. So this interval, right, over here, where the output voltage is 0. Again, integrated over a dummy variable. So right away, we can see that, we can see two things. One, this goes to 0, right? We're integrating 0 over some interval. We're integrating a constant 0 over an interval. That integral must be 0. Secondly, this is a constant voltage, so we can just pull it out, right? We can pull it out and we integrate 1 over some interval. So if we evaluate this, I'm just going to continue up here. If we evaluate this, then V out of t averaged over some switching period is simply equal to 1 over Ts. And again, we're integrating 1 from 0 to dTSW times VBAT. So this integral evaluates to VBAT times dTSW. Right? You can do the math if you want to. You can solve this integral more completely if you would like. I don't want to. And again, we can cancel out these TSWs, and then what we end up with is that the average output voltage is equal to D times VBAT. The average output voltage is equal to D times the input voltage. So again, because D varies between 0 and 1, that means that this average V out varies between 0 and VBAT, right? If D is 0, then the output voltage is 0, and if D is 1, then the output voltage is VBAT. So by controlling D, so let's just highlight this, by controlling, do you want a different color? How about this color? So by controlling D, the pulse width we can control the average output voltage. So we can control the output voltage via So this is known as pulse width modulation. Right, so we can control the output voltage simply by varying how long the switch is on in relation to the full switching period. So the longer it's on, the higher the output voltage, the shorter it's on, the lower the output voltage, the average output voltage, right? So that's cool. We can now control our output voltage simply by controlling how long the switch is on. When the switch is on, it doesn't burn any power. When the switch is off, it doesn't burn any power. So currently, we're not burning any power by doing this. However, we're still not done, right? We still have some problems, right? So let's just redraw our output voltage. So again, we have this square wave. We found the average is great, right? The average is exactly what we want. We can control the average by controlling this pulse width, but there's a problem, right? This isn't a DC voltage. It still isn't a DC voltage. We haven't solved that problem. And in fact, if we think about the Fourier series expansion of this signal, and we plot the frequency components of the signal over frequency, right? Then we notice that we get our average at 0 frequency, right? That's great, that's perfect. But we have all these harmonics at multiples of the switching frequency, right? Again, you can look at the Fourier series expansion of a square wave, but it's something like it falls off with 1 over n, and the harmonics are all at multiples of the period of the frequency of the fundamental frequency of the square wave. So we have harmonics at FSW, 2 FSW, 3 FSW, and these are the things we don't want. If we got rid of these high frequency components, then we would just have what we wanted. So if we get rid of these, we're good, right? We've done what we wanted to do. We've made a controllable DC voltage without any AC component. So how do we get rid of this? How do we get rid of this stuff? Well, I mean, just from this picture, what should come to mind is some kind of filter, right? We have some kind of brick wall filter, some kind of low pass filter. We need a low pass filter, right? Right? Because we want to keep our DC component but eliminate the high frequency components. Right? So we need a low pass filter to do that. And if we do that, then we're home free. So how do we make this low pass filter? Well, again, going back to circuit theory, what might come to mind is this. This is an LC filter. And the reason we're using an LC filter, it doesn't have any resistors. No resistors, right? An RC filter has a resistor, an LR filter has a resistor. We don't want that. So what we can do, right, I hope you guys remember how this works, but for those of you who do not, what we can do is convert this into the phasor domain, right? We can think of phasors, frequency-dependent signals, or we've removed the frequency dependence of these signals, so they're kind of constant over certain frequencies, but these elements, L turns into j omega L, and C turns into 1 over j omega C, and these are the impedances of these components, right? J omega L is a frequency-dependent impedance of an inductor, and 1 over j omega C is the frequency-dependent impedance of a capacitor. And we want to relate the amplitude, or the magnitude of the input phasor, which I'll denote with a little line underneath V, to the output phasor, V2. And if you're thinking that it looks similar to a voltage divider or a resistive divider, it is very similar to a resistive divider, right? We have two impedances, and the output is across one element of these two impedances. So we can find a relation between V2 and V1, V2 over V1, and it turns out to be something like 1 over 1 minus omega squared LC. And from this, we can notice that there is some cutoff frequency, f naught, which is 1 over 2 pi root LC. And in this case, Q, which isn't related to a switch, it's the like the resonance, Q tends towards infinity because there's no resistance. So we can plot this. We can give a Bodhi plot, right? So we can think of this as like h of j omega. And we can plot the magnitude of this filter, right? And if you remember how to draw this stuff, well, we have our cutoff frequency, f naught. And at low frequency, the gain is 0 dB. In this case, we have some resonance because there's no resistors in here. But then it starts falling off after f naught with minus 40 dB per decade. So if we choose this appropriately, then we can filter out the high frequency components and keep the DC, right? There's 0 gain at DC and high frequency components are attenuated. Perfect. So if we just stick in this filter into our previous circuit with this one switch, this is what we get. However, there is a problem, right? And to understand what that problem is, we have to look at this inductor current, IL of t. Right, so let's plot this over time. So what we have to do is imagine we're turning on the switch for the first time. Okay, so nothing is energized. We're plotting IL of t over time. Cool, so at time t equals 0, the inductor current is 0. We apply some voltage to this inductor, right? You can imagine that there's some voltage across this inductor, VL. So when we turn the switch on, VL is equal to VBAT, right? Because the output voltage is 0, which means that, again, VL of t is equal to L DIL of t dt. So if we apply some positive voltage, then the slope of the inductor current is going to be positive, which means the inductor current is going to rise up, right, with some slope. So it's rising up, rising up, rising up. We're increasing the current through this inductor over time. And then the special moment happens, right? We get to dTSW, where we switch Q off. So what happens here, right? What happens at this moment, right here? So we can imagine that it reaches some current I. So right here, we switch Q off. What happens? Well, just before this time, right, just before dTSW minus, the current is I. And then just after this moment, dTSW plus, the current needs to be 0, right? It needs to go to 0 because this is an open circuit and there's no place for the current to flow. It's got to be 0. But together, what does that mean? So this is kind of like happening over a very short period of time. This means that the derivative of the current must be extremely high, right? It's changing from some current to nothing in no time. So that means that the derivative of the current tends towards infinity, or negative infinity, whatever you want to say. It tends towards some huge number. You're changing the current very quickly from something to 0. If we think back to this equation, if the inductor current derivative is really huge, it means that the output or the voltage across the inductor must be enormous, right? Because it's just some scaled version of the current. That means that VL of t has to tend towards something huge as well, because the slope of the current is really huge. So basically, what's going on, if we turn off the switch while there's some current through the inductor, there's going to be a huge voltage spike. Which a lot of times is catastrophic. So this results usually catastrophic failure. This usually results failure. Okay, let's just hope that's right. This usually results in something bad happening. So we need to add. We need to add something to make this work. And what we need to add is another path. We need another path. So basically, to summarize, so given all this stuff, given all of this, we need a path for the current to flow. We need somewhere for this current to flow when Q goes off. And it turns out what we do is we add a path to ground. We allow the inductor to draw some current through the ground terminal, let's say, right? So we allow this extra path. If we do this, this is what we get. And this is what I showed you before. This is the buck converter. We got there, right? We somehow derived a buck converter by thinking about a resistive divider, using a transistor as a switch, and then kind of filtering out the high frequency components, and then adding an extra path for the inductor current to flow. So this was kind of a unique path, a unique way of deriving a switch mode power supply. Most converters can't really be analyzed in this way. The buck converter is kind of unique in that, right? All we're doing is we're chopping up a DC voltage, creating an AC waveform with a DC component, and then filtering out the AC components to get a constant output voltage. Okay, so how does this work? Well, again, we still only have two states, right? These are the two states. In one state, from times 0 up to DTSW, Q1 is on and Q2 is off. So again, the voltage here, the voltage at the input of this filter, and this node is very important. Often we call this node the VX node, or the switching node. VX is equal to the battery voltage, right? So it's doing the same thing that it was before when we only had one switch. And this is often, so sometimes people refer to this switch Q1 as the main switch. So main switch, or MS. And sometimes you can refer to this state as like the main switch state. Some notational stuff, some jargon, but yeah, basically this first state is when the main switch, Q1, is on, and the switching node voltage, VX, is VBAT. In the second state, Q1 is off and Q2 is on, right? So and this occurs, again, very similar to the previous case. So this occurs when time is between DTSW and TSW. And again, remember that this repeats in intervals, right? So when this period ends, we go back to this state, right? So we kind of alternate between these two states. And here, the VX node, again, very important node. The VX node, the switching node, is 0 volts. Right, so this is kind of drawing out that waveform we drew before for the output voltage. But now it's the switching node voltage. And after the switching node, we've placed a filter. Cool. So sometimes, again, just for your reference, sometimes this Q2 is referred to as the synchronous rectifier. Probably spelled that wrong, but whatever. The synchronous rectifier, or the SR. So sometimes this is kind of referred to as the SR state. Okay, cool. So this VX node is alternating between VBAT and 0. So VX, this is the switching node. This is like the all-important node. This is where all the magic is happening in a switch mode power supply, right? Switch mode, the switching node is the important thing, right? So you can kind of like zone in when you see a converter, you can kind of zone in on that switching node or the nodes that switch, because there might be more than one. So yeah, basically you just alternate between these two states, between state 1 and state 2, And again, we haven't really changed. If you think about the average of Vx, the input to this filter, if you think about the average of Vx, it's the same as the average of the output voltage that we derived before. So what we can write is that the average of Vx of t is equal to d times V bat. And as a result, if we're filtering out the high frequency harmonics, it means that V out is equal, or like the average, the DC component of V out, we have some filtering, is d times V bat. So we got what we wanted, right? This voltage, this buck converter, what it does is it scales the input voltage by some factor d. And we control the output voltage by varying d, varying the pulse width of the square wave. And in that way, we can control voltages. We can step down voltages in a controlled way. One thing I should note, there is a not allowed state. We can't have Q1 and Q2 can never be on at the same time. Why? It's a short. It results in a short circuit, right? If Q1 and Q2 aren't at the same time, then you're shorting out the input to ground. We can never do that. So there's a disallowed state in this buck converter. Either Q1 is on and Q2 is off, or Q2 is on and Q1 is off, but never on at the same time. Sometimes even both of them can be off at once. Right? Q1 and Q2 can be off at the same time, but nothing is really happening in that state, let's say. We'll get there later, but yeah, just note that Q1 and Q2 can never be on at the same time. So this is like, I just wanted to introduce this way of producing the buck converter. So we started again with a resistive divider. We decided to not use resistors. We decided to use the transistor as a switch. By doing that, we created a waveform with an AC and a DC component, right? So what we ended up with was a waveform that was a square wave, right? And this square wave had some average. And the average was what we were interested in. So we filtered out the high frequency stuff just to get the average, right? Alternating between two voltages to filter out and filtering out unwanted components. And we can control the output voltage by varying this pulse width. So as we vary the length of time Q1 is on, we can change what the output voltage is. Right? So that, again, this is kind of like a unique way of analyzing a switch mode power supply. You know, even if you weren't studying power electronics, you could kind of conceptualize how to do this, right? Maybe if you like someone who is studying like signals or analog electronics or something like that, they could kind of think of this as well, right? We create a square wave, we filter out high frequency components and keep the DC. Super simple, right? But not every converter can be analyzed in this way. And we're going to need a different set of tools to analyze them. Namely, those tools are the concept of steady state operation, which is kind of like, it's not constant, but it happens regularly. Like the state of the converter happens periodically and regularly. We'll get a more precise definition later. The idea of small ripple approximation. So we're kind of, eventually what we're going to do is ignore some high frequency components in signals. And then the ideas of inductor volt second balance and capacitive charge balance. And using these things, so these are kind of like simplifying ideas. These ideas simplify how power converters work, or how switch mode power supplies work. They make it easier to analyze. And these two ideas let us solve for DC components. Let us solve for DC values of things. And that is kind of a critical concept, right? Because that's what we were doing with the buck converter. We wanted to know what the DC voltage of our square wave was, and these tools allow us to do that. So that's what we'll do in the next lecture. And yeah, I hope this was clear. If you have any questions, please, leave a comment and we'll discuss them. I've also included some material for you to practice. So you can average some signals over a switching period. You can also find the RMS of some signals over a switching period. And yeah, I'll see you guys next lecture. Thanks.